Hi, today I'm going to start to talk about how to use the OCEANLYZ. OCEANLYZ is a toolbox that originally developed in MATLAB for analyzing the ocean wave data. Later on, the support for Octave added to that, and then from the version 2, this support for Python also added to that. So you can head to my own website to get the latest version and the helps, or you can go to the documentation webpage under read the doc and get all the information about the latest version and all the help about how to use it. Before I start to talk about it, first it says it needs MATLAB, so it's gonna either says, as I said, it's gonna use MATLAB originally. If you don't have access to MATLAB, you can use the Octave. So it's a free open source alternative to MATLAB. It's not as powerful as MATLAB, but it can do the basics. And as I said, the OCEANLYZ is write in a way that it's coded in a way that is work with the Octave. Or if you're working with Python, you can use the Python to work with that. In this tutorial, later on when I start to show what I use the Octave to show you how to run the MATLAB version, and then for the Python version, I use the Anaconda Python as a Python version, and then I use the Spider IDE to run the code in Python, in case that when you see it, you wonder what it is. In addition to MATLAB itself, if in the OCEANLYZ there are two methods of the analyzing data. So one of them is um, signal processing, and the other one is the one of them is the spectral analysis, and the other one is zero crossing. If you're using the zero crossing, you don't need any additional packages. But if you do spectral analysis, then for the MATLAB you need to have the signal processing toolbox, and it doesn't come standards with MATLAB, so you need the additional license for that. If you are using the Octave, then Octave also you need to have the signal package. The good thing about Octave is that the signal package comes with it, but it does not load automatically to the Octave. So every time you run the Octave, you have to load the signal package. In case for the Python version, what packages you need? So if you run it on use it Python, you need to have the NumPy that is used for array to work with the array. Then we need the SciPy, basically it's working mainly with the spectral analysis needed there, and you need the matplotlib for plotting the data. If you're using the Anaconda Python, these three packages, the NumPy, SciPy, and matplotlib, already are included in the Anaconda Python. If you're using the standard Python, then you have to go ahead and also install NumPy, SciPy, and matplotlib on that in order to use the OCEANLYZ. So before I start, whenever you download the OCEANLYZ, you're gonna get the folder, and if you unzip it, this is something that you are gonna get is the OCEANLYZ class, or the main file which do the everything is that. And then you have folder that has the document in there. There are functions that the OCEANLYZ uses, and then there are some sample files that you can use to just play around with the OCEANLYZ, and today I use those. So one more thing about MATLAB version, as I said, the MATLAB version comes as a zip file, and when you unzip it, these are the files you are gonna get. And whenever you want to use them, you have to make sure that your working directory in MATLAB is wherever these files are, or other word, these files should be in your working directory. If your work directory is somewhere else, just simply copy all these files and subfolders into that directory so MATLAB can find OCEANLYZ. Or you can simply add the path of wherever these files or folders are, just add the path to MATLAB, so MATLAB always knows where it needs to look for OCEANLYZ. It knows where to look to find the OCEANLYZ and find it. If you are using the Python version, instead the Python version comes as a package, and you install it and you import it as a library, so Python always can find it, so you don't need to be worried about that, and I will show you later how to use that. If you want to use the Python version of the OCEANLYZ, remember the Python version of the OCEANLYZ is part of the Scientimate package, so you have to go ahead and install the Scientimate package. So you have to have the Python installed, and then you have to install the Scientimate package, and then you have access to OCEANLYZ through that package here, and you can go ahead and later on show you how to use it, but this is how it's gonna work. So the MATLAB version is gonna be a standalone toolbox that you download it. If you use the Python version, then it's gonna be part of the Scientimate, and you have to install the Scientimate before you can use the OCEANLYZ in Python. Before I tell you how to use it, first I will go ahead and tell you what are the parameters you have to set up every time that you run the OCEANLYZ. The OCEANLYZ is it would be like the class, and so you don't need to be worried about how it works, but basically every time you call it, it loads all the default parameters automatically. So every time you call it, all the default parameters is loaded and is ready to go. If you don't want any of those default parameters, you have to go and set it with the new values. If you don't change it, you just simply use the default parameters to run the code. So I will go ahead and do that. Some of the parameters are required. You need to set them up, and you have to basically define them. The very first thing is your data, and the date is the data that you're gonna analyze. It can be the water level. It basically can be the water level. It can be the water depth, or it can be the water pressure. And it's a time series, so it's gonna be in one of these format. Remember that whenever you have the data, all the data should be as a single. If you are using a MATLAB, it should be a single column array, just one column. And if you are using it in Python, it should be 1D array. So here, when I load it, I will show you. But here, for example, let me open one of those sample files. Here, if I open this, you can you can see that all the data is a single column. So you can see here it's just single column. So everything is just one column. So all the data is single column, regardless of how many data points you have. The single column data, use it at that. If you're in Python, just use it as a 1D array. So to make sure there's nothing, everything goes smoothly. The second thing is the input type. Basically asks you what's the input type. If your input type is water level, or what else is the data, is the water level or the water depth, you just set it as input as equal to water level. If the input type, the data, if your data water pressure, just set it as pressure, so it knows that what type of data is using. Then the next thing is the output type. What do you want it to calculate? Do you want it to calculate the wave? If you have the pressure data, you want it to calculate the water level from pressure data. And if you have the pressure data, do you want it to calculate wave and water level from the pressure data? So basically, if you use this one, it means that your input is either water level or water depth. But if you use either of these two, it means that your input data is the pressure data, should be a pressure data to use that. The next thing is that what method you want to use it. As I previously said, that if you can use the spectral analysis, or you can use the zero crossing method. If you use the spectral analysis, then you need to have access to the signal processing toolbox in MATLAB, or you have to load the signal package in Octave, or in Python you have to have the SciPy also installed. The Number of bears, it defines how many bears you have. So I have another video that explains exactly what is the continuous measurement of bears measurement. But let's put it this way for just a very simple example. Assume you measure 5 hours of data, and particularly when you're measuring the data into, for example, the open ocean, because of the tide, the mean value of the water depth is going to change. So you have to analyze data in shorter period. For example, you have to analyze data every 1 hour. So we measure 5 hours of data, then we want to analyze data for every 1 hour. So if we have 5 hours of data and we want to analyze it every hour, basically we have 5 blocks of data or 5 bears of data. So we are putting 5 here. It means that well, whatever number you put here, it tells the OCEANLYZ go and divide the whole data set into that number of blocks of data. So for example, you put it 5 here, it divides the entire data set into 5, and it grab each of them for it grab one block and analyze it, and then goes and grab the second um, block and analyze it, and then third block and analyze it, and so on. So that's the number of bears. And then the burst duration, for example, here it says we have 5 hours, and we assume we want to analyze every hour separately. So the burst duration is 1 hour, or basically 3600 seconds. So it's the duration of every block of data we want the code to analyze. And the sampling frequency is the frequency that the data are measured at those frequency. It's important to remember that if you're using the spectral analysis, all the analysis is going to be between 0 and half of the sampling frequency. So every value used set in the code should be between 0 and half of the sampling frequency. So for example, if the sampling frequency is 2 here, every value of frequency comes out from the spectral analysis is going to be between 0 and 1. Half of the is between 0 and half of the sampling frequency, which is going to be 1. So up to here are the variable we need to define them regardless of what we want to do. From here on, some of them only required for a specific task. For example, these two only required if we are using the spectral analysis, and it tells which part of a spectral we want to keep. So Fmin means that the minimum frequency to keep in the analysis, and Fmax means the maximum frequency used in the analysis. So anything less than Fmin would be considered as 0. Anything after Fmax would be considered as 0. So why we need to do that is that because always when we are doing the spectral analysis, there are the lower frequency and higher frequency. Generally you have some noise in the lower part of the spectrum and the higher part of the spectrum, and you don't want to keep them in the analysis, so you will remove them. Remember, the Fmin cannot be less than the 0, but usually you don't want that very small values, so you probably leave out some of the very low frequency noise values, which are the noise. The same thing for the high frequency. This cannot be larger than half of the sampling frequency, so it should be smaller than half of the sampling frequency, but in most cases we keep it smaller than that number, because when we get close to that to high frequency, the data would be contaminated with noise, and we don't want them. One way of knowing that which part of the spectrum we probably don't need is that just put the 0 for Fmin and put the half of sampling frequency for Fmax, run it and look at the spectrum, and then look which part of the spectrum visually. If you look at it, you will see which part of the spectrum is not right, and probably there are noise, and then come back, set this limit, and rerun the code again, so you get rid of the noise at the lower and higher frequencies. And again, I said you need them only if you're using the spectral analysis. The next part is that if the input data or pressure data, we need this part, otherwise we don't need to set any of the following values. And the reason is that, again, I have another video explaining why we need to do that and how to do that, but in very short is that whenever we measure the water surface elevation or the wave with the pressure sensor, we need to put the pressure sensor somewhere. Mostly we put it on the seabed or under the surface, and it's a very convenient way to do that. But the problem with pressure sensor is that the energy from the wave attenuate and dissipate when it goes down in the water column. So whatever the pressure sensor measures, whatever energy pressure sensor measures is less than actual energy at the surface, because some of the energy is gone before it reaches the sensor. So we need to actually go ahead and compensate for those energy. Otherwise, if we don't compensate for the energy loss, the values we are going to get for the wave height is going to be smaller than actual wave height. So before explaining these two, first I will explain these two. So the problem is that when we want to analyze the wave data, pressure data, as I said, we have to compensate for the energy loss, but usually we don't need to compensate for the very low frequency, because those low frequency associated with a very large wave, and then most of them they don't lose much energy. Also, we don't need to compensate energy for the energy loss of the very small waves at the very high frequency range, because otherwise, if we do, we are gonna artificially make the wave larger than what it is. So we are not correct the small value, a very small frequency, the value for the small frequency, and we are not correcting the energy for the very large frequency, for high frequency. We just remove them, we don't want them. These two limits just tell the code what's the range that you want the pressure attenuation corrected, what the energy, the data is corrected for the energy loss. So now I come back here is that the ways that, okay, how do you want to calculate that range, the higher range, basically this part, how do you want to calculate that? And so it's a little bit tricky to exactly how far you need to go in the higher frequency. So I would say that unless you exactly know what the value you want, just leave it as an auto, let the code calculate how far it should go to correct the pressure. Otherwise, if you know exactly how far you want to go to correct the pressure, you can define it as a user, and if you define it as a user, basically tells it use this value for every for the upper limit. If you put it as a automated, then it's in the automated, it considered this as the upper limit. If it is less than that, it use it then. But if it's larger than that, it's going to be limited to that. So I would leave this into auto. Always let the code decide what part of the spectrum you need to correct for the pressure loss. And then is that also when you reach to this value, you have to tell the code what to do for the frequency that are larger than this. And one other is that you can tell it to do no change. I do suggest to do that. It means that keep if you make it no change, it means that keep correct the pressure attenuation, keep correct for the energy loss for all the smaller energy as well. And most likely you are going to get the wrong answer. Except for very few cases that you may need to go the all range, you don't need to use this. So basically it tells your code go all the way to the uh, largest frequency you have. If you put it as 1, it means that you go all the way to this, correct it up to this point, and after that just don't correct it. This is what it means. And if you use it as constant, it means that go and correct it up to this value, and after that use whatever value you have for the energy correction at that frequency for the larger frequency. And probably this is the best option. So you tell the code, indeed, if I use it auto and constant, it means that it tells the code start from this point, try to find this one, and when you reach that point, for the frequency larger than that, just use the same energy correction. The height from bed also just tells the code what is the from what height the pressure sensor sits above the bed. So it needs to calculate these values. It needs to be calculate the pressure response values. So I would say that most of leave this at auto. Let the code decide the range that the pressure you need to correct the pressure, the range that you need to correct the energy loss. Use this to apply for the very large frequency. Just apply the constant values. This is the lower limit that's going to be pressure loss is applied to that, and this is the higher limit that the pressure energy loss is applied to that. Again, I said if it's constant, after that the pressure loss, the constant correction would be added to the to correct the pressure loss or energy loss. And you need these only if we do pressure data, if we have the pressure data. Otherwise we don't need any of these. So the rest are very the rest of the properties are I would say optional. You don't need them. So these ones just tell if it plots the data when it's analyzing, plot the data or not. The next one is the density of water, and if you use the pressure, if the input is the pressure data, the density of water is needed to convert the pressure data to water depths. So for the fresh water is 1000 kilogram per cubic meter. For salt water is about 1024 on average, something like that. So if you need to change it, change it. This one tells how many data points is going to be used when it calculates the spectrum. And so the larger is that, the more smoother spectrum you get, but it's going to be computationally more costly. 512 is probably, or 256 or 512 is probably the best numbers you can use. Anyway, whatever number you use, make sure that you use 2 to the power of n. So it's going to 128, 256, or 512, or 1024, or something like that. So make sure you have it that way, and also make sure it's not bigger, it's not larger than the number of sample points you have. So if you, for example, you have 1024 data sample, so make sure this number is equal or smaller than that. Then the next part, that these three values, it basically tells if to separate sea waves from the swell waves or not. If whatever waves is generated locally, we call it the wind sea. So it's the locally generated waves. If the wave comes from outside the area that we are working, it is considered a swell. So for example, if you are in the Gulf of Mexico, Whatever waves is generated inside Gulf of Mexico is going to be locally generated wind, and it's going to wind C. Whatever waves comes from the ocean into the Gulf and it's not generated locally, but it comes from the ocean, it's going to be the swell. So if we have in this case, we may need to separate them to know which one is local generated, which one comes from the outside the area. In that case, so we can come here and set it to separate it. If we set that to separate this sea and swell waves, then we have to define the range that we have for the swell waves. So in case that it's not going to make a mistake between sea and swell, so can only use these two if we have this equal to yes. Also, the last three parameters that you can use is that if we have the spectrum and we know for some reason the tail of the spectrum, the values for the very high frequency, the high frequency value in the spectrum, we don't have them, or we know they are wrong, we can go ahead and replace them with one of the available empirical spectrum. So just remove the bad data we have and replace it with the empirical values. We can only use it for the tail of a spectrum, and don't do that unless there is no other way, unless it's real necessarily. So if it's off, it means that leave the data, it's not gonna change anything, or you can put it as a John swap or TMA. If you equal it to John swap, it's replace the tail of the spectrum with the John swap tail, or do the TMA, it use the TMA spectrum, the tail of the TMA spectrum, and replace the tail of the spectrum with that. Generally, John swap is more suitable for deep water and TMA for the shallow or transient water. If you use this as, if this is off, you don't need to set any of these two, but if it's not off and you tell them to replace it, then this value tells the code from what point you want to replace the tail. So where's the location that after that you want to replace the data with the tail. And again, remember, it's always going to be after your peak frequency. So your spectrum go up to the peak and you go to the tail, and then some part of the tail you want to replace. So this is the location of that. And also this is the slope of the tail. So you would say that what slope you want to have your tail. Usually the -5 is suitable for deep water, -3 is suitable for the shallow water, and the -4 is more suitable for the transient water. After these are the properties, or basically the parameters of how to run the code, and then we can use the run OCEANLYZ method to run the code. I will show you later on how to do that. And then we have the output is going to be as a structure array. If we are using the MATLAB or Octave, it's going to be a structure array, so everything is saved in a structure array, and I will show you how to do that. But here, for example, the wave height is going to be, for example, the object dot wave, which is going to be our output dot HMO, and I will show you how to. The only difference, there's a difference between here and the Python version. So here is the structural array. In the Python is gonna be the dictionary. So the output would be in dictionary. So I will show you how to call them as an example. So I will go ahead and show you the example how to run the code in the example. Before I run it, first I will go through that. The very first thing, as I said, you have to be in the folder that the OCEANLYZ data are there, and then here I just load the data and I go back to the OCEANLYZ folder. So that's all I'm gonna do. Save the current folder, which is the OCEANLYZ folder. I go to the sample folder, or wherever you have the data. I read the data, and I go back again to the OCEANLYZ folder. Here, if you need to plot the data, input data, you can plot it. So I show you how to plot the data. And from here is that after the data is ready, the very first thing is that we have to create the OCEANLYZ object, and it's just as simple as that. Right? Just for example, I call it OCEAN. You can call it whatever you want. So OCEAN is equal to OCEANLYZ, and it creates the OCEANLYZ object, and it loads all the default parameters. So right now the OCEANLYZ is there, all the default parameters gonna be there and it's gonna be ready to run. Then I assign the water pressure, the data that we just create here, to here. So I can say OCEANLYZ.data is water pressure. So this says the data is gonna be set. And then here I set up some of the parameters. So input type is going to be pressure. I know output type is going to be wave and water level. And remember, every of these is like that. The object dot parameters and equal to whatever we want. I want to use the spectrum analysis. As I said, the data I show you is the file. It has a 5 years of data. The data here is that just explain how we have the data is that what we set the data is that we set it to measure the data for 5 hours, but the sensor, we didn't set it to measure continuously throughout the 5 hours. So it was like that. The sensor wake up at the beginning of the hour, it measure for 10-24 seconds, which is about 70 minutes, and then it goes to the sleep. At the start of the second hour, again it wakes up. It recorded for 10-24 seconds, and it goes to the sleep until and it repeated at the third hour, at the fourth hour, at the fifth hour. So we have 5 blocks of data. Each of them is 10-24 seconds, and each 10-24 seconds represent 1 hour of the data. So we have 5 bursts. Each of them is 10-24 seconds, and we measure them with 10 Hz frequency. The sensor we had, the pressure sensor, sorry, not this. The minimum and the maximum is that for the mean, I don't want any of the values is less than 0.05 Hertz, but I will go all the way to half of the sampling frequency, which is going to be 5, and this is the maximum I can get. I can't limit that if I know I have a problem in the higher frequency, but in this data we don't, so I can go all the way to the half of the sampling frequency. Again, because these are the pressure data, I have to compensate for the energy lost from the water surface to the location of that sensor. So I would put it there. I said, okay, plus calculate the range calculate the range of the frequency or basically calculate the higher range of the frequency to be corrected for the pressure loss. When I set it as auto, the code would automatically consider that. The constant means that for the larger frequency, just use whatever you find for the maximum, whatever value you use for this frequency. These two are the range of the frequency is going to be corrected for the pressure attenuation. Remember, because I put this in auto, this one only use if the one that's calculated by auto is going to be larger than that. Otherwise, the one that's calculated by code is used. So because it's at auto, this is going to be the larger limit, the higher limit of that, but the actual one might be smaller than that because it's calculated auto. If I put it as user, this is always going to be the higher limit. So that's the difference between this one be auto or user. If it's user, this is going to be the upper limit. If it's auto, it's automatically calculated, and if it is less than that, it use that. If it's larger than that, it use this. And our pressure sensor sits about 5 centimeters above the bed, so what we put 0.05. I want the data to be shown when it's analyzed, and where we were analyzed data, the the where we measure the data, the uh, water density was about 1024. So you can set that as well. And after you set up all the input parameters, all you need to do is just object.run OCEANLYZ, and it will run it for you. That's it. And then I will show you how to grab some of the data, how to plot the data. So first I will show you how to do it in Octave. So it says the Octave has the signal processing tool. It comes with the signal processing signal package, but you have to load it every time you run the Octave, otherwise it gives you an error. And because here we are using the spectrum analysis, I have to load that. If you use the MATLAB, you have to have the signal processing toolbox. So if I go ahead and run this part of the code, basically what's going to happen is just go to the OCEANLYZ folder, and it read the data. We change the work directory to OCEANLYZ folder, and then we read the data. And remember, so we have to be always in the OCEANLYZ folder. So if I run that, you will see it goes there and it just read the data. So the data is read there, so I can plot the data. If I run this part, it will plot the data. See, these are our input files, and as you can see, the pressure just keep increasing. It means that the mean water level during the measurement keep increasing. That's because of that we have to break it into the smaller part when we want to analyze it. That's why we use it. Then here I will just run this part. It means that I create, if I run it, I create the object. So if I run the selection, you'll see that it will run. If I just click on that, it will tell you it's the OCEANLYZ object. So it created an object and it loaded all the default value. And then from here, I can load the data. So I would say the data. For example, here, if I say .data, it gives you an empty array. So there's nothing there yet. So I can go there and run this part, and it upload or assign the pressure data read into the OCEANLYZ data. And then I will run this as to set these input parameters. So all those input parameters will be set, and now I can run the OCEANLYZ just by running that line of code. So it will run, and it will show you those. So these are the spectrum. So it's a 5 spectrum because we have fibers. So one spectrum for each of them, and these are the spectrum of the fibers. If you go back, when you run the OCEANLYZ, it's gonna start giving you some information. So it tells you what version is this, and just gives you some of the, it tells you all the values right now it's using. It doesn't mean that it's use all of them. It just tells you what are the parameters are right now set to. So you can go ahead and look at and see what are the parameters are set to. After that, it tells you, and this part is very important, just it tells you what it is doing and what input data it expects you to give it to it, and what output data is going to tell you. So make sure you read always this part to make sure it's exactly doing what you want to do. Otherwise, you have to go back and change some of the input parameters in order to get it to do exactly what you want. Then you have this, it gives you the information or calculation for each burst of, for example, here some of the important. So it's a wave height, for example, or there's a peak frequency. So it's a zero moment wave height. And then it tells you what are the outputs, and basically all the outputs that you have the water surface, zero wave height, peak frequency, peak period, peak frequency spectrum. These field names is contained all the field names that you want. So if you forgot what are the field names you have, you always can get that. So remember that, for example, to get anything, so we call to get the field names, if you forget, we write the object name dot, and then here as I said, all the outputs is going to be in the wave structure array. and then we call the field names, and just gives us all the field names. So this is how we do. If you want to get, for example, the wave height, that's all. For example, I will say h is equal to OCN dot wave. So OCN is the object, dot wave is the structure array that contains all the data, and then dot HMO, which is here, you can see it, is the one that contains the wave height, and I can plot it. So it will plot the wave height for me. The same I can, for example, goes here and say if I want the frequency and the spectrum, I say so okay, because I have one other parameter I have, this the frequency here, you can see. So I can say f against the OCN dot wave dot f. So it gives me 5 data, you see, and each of the, for each burst is going to be gives you one row of data. So each row represent one burst of data. The same we can use for the spectrum dot, and then we can plot it if we want. For example, for the first one, so we are going to have the first row for the first burst. So we just draw the first row, and it plot the spectrum for us. You can plot it right like that, but usually I would say it's better to plot it in log scale. It gives you better idea of what's happening. And as I said, for example, when you look at it, for example, you may say, okay, this part probably is not good, this part probably is noise, and you want to get rid of that part. So you can set the f max in a way that you don't get this part of data. So this is how you can access each part of the data. Or if you want to the whole data set, for example, the wave, you can say OCN.wave, and then you can have the structure array that has all the data in that. So you can work with that. That's how it works in MATLAB or Octave. Running OCEANLYZ in Python is very the same like that we did it in MATLAB, just a few differences. One of the things that first in Python we need to import the libraries. So these are the libraries we have. We import. We need to import the scientimate because the OCEANLYZ in the Python version of the OCEANLYZ is part of the scientimate package. So first we have to import the scientimate package in order to work with that, and so we import the scientimate, and then we import the OS. We import the NumPy, which lets us to work with the array, and we import the matplotlib, which lets us to plot. So these are the 4 libraries we have to import. So I will import them before I start anything, and then I just read the input file here. So I have that input file. I can plot it to see what the input file looks like. So you can see that the input file look like this. So we can have that input file, and then we can, after that, we will generate the OCEANLYZ object. All the differences that we have, as you see here above here, we import the scientimate as sm, and then we have sm dot OCEANLYZ, with that sm just stands for scientimate, and then we says that go and run the OCEANLYZ module inside that scientimate package. So we just run it like that, and it's going to create the OCEANLYZ object for us, as you can see it here. And if I put this here, you can see it says that's the OCEANLYZ. And then we can, the data, it just create a very default OCEANLYZ object. If I put the OCN dot data, you will see it's empty, there's nothing in there. So I can, by running this line, assign the data to OCEANLYZ, and then I can assign the other input parameters here, just running the lines similar to what we did before, and then by running this line, it runs the OCEANLYZ, and just start running it, and then we can see the results. So these are the, because we have 5 pairs of data, so we have 5 spectrums, so these are the spectrum from the results, and here you can see it printed out the information about what it did, all the input parameters, and it says it's not going to use all the input parameters, it just says what are the input parameters are set to at the moment, and then the information for each burst, and then the output values. Again, it says if you want to know what are the, because the difference between here and the MATLAB version is that everything here is a dictionary, and to find the key name for the dictionary, we can just say OCN, which is our OCEANLYZ object dot wave. Everything is stored in the wave dictionary, and then we can type the field names, and it tells us what are the field names it stores, and so it gives some warning here. And then these are the field waves we have the water surface, 0 moment wave height, peak period, peak frequency, and the rest. And then similar to that, we can, for example, if we want to assign the 0 moment wave height, we can say this is OCN dot wave, and then HM0, and it's going to assign it to that. So we will see it's coming up here, you can see it, and we can also plot it as, so these are the wave height we have here. Similarly, we can get the frequency, and so it's our object, so our dictionary is a wave, and then the key name of the dictionary is the frequency here, and we can assign it to f. So we get the f. As you can see here, we have 5 bursts of data, so each row contains the data for 1 burst, and then we can, similar to that, we can have the spectrum data assigned to SYY, so we can have it here also, it is a form, and we can plot it. So plot, I'm going to plot the first row, each of them, so it's going to be the data for a first let's say the first burst of the data, So if I plot it, so it's a spectrum of our data, you can see it. Again, it's easier to plot it in log plot, so you can go ahead and do it in log, and so you can see better what's happening in your plot. And so if you know that probably you don't want anything before here, and you don't want this part also, you probably want to remove these 2 parts from your spectrum to get a more accurate result. So this is how we can use the OCEANLYZ in MATLAB and then here in Python.